in the relays and contactor sections, I've published or made available to you guys in-class schematics 1, 2, 3, and 4. Okay. And then down further, there's going to be, I don't think I made them available yet because I want to go over this stuff first. There's going to be schematic 7 and a 5 and a 6 someplace. And again, I'll make those available probably later today for you guys. But the 1, 2, 3, and 4 that is in the relay and contactor section, I do want you to download. Because that's the ones we're going to start using on the pictorial side to talk about motors. So flipping over to my PDF Expert, and again, this is the same tool you guys have. Okay, I'm just using the version on the Mac just because of screen size, what I'm presenting to you guys. So our first schematic of the day, okay, was on Monday. It was a very simple schematic that I was asking for a line voltage schematic that consists of 3 light bulbs. 2 bulbs are wired in series, and the third is wired in parallel to the 2 in series. A single pole switch controls the whole 120 volt circuit. A second switch will then bypass the second bulb in the series. Now, I did go over this yesterday, but I still, for some reason, I don't think we might not be totally getting it, maybe because people aren't asking questions as I'm doing this. But to redraw this schematic, okay, it's basically a ladder diagram, okay? And we start off with, we have one switch. I have a service switch that's controlling the whole thing, so let's put in our service switch. Okay, so I have a switch up here that's going to be controlling the whole thing.
You okay, baby?
And then I have, I'm going to start off with the simplest portion of this, the bulb that's in parallel with the other 2.
Okay.
And there is someone talking in the background to someone else, so I'd really appreciate if you'd mute yourself. Okay, so then we have the single pole switch controlling everything. I have 1 bulb. This will end up being bulb 3. And then I have 2 bulbs that are in series. So let's toss those in here real quick. Okay, so we have 2 bulbs that are in series, and I'm going to label all this when I'm done drawing. Now, we have a single switch that is a bypass to bulb 2. Okay, all a bypass is doing is providing a path for electricity to flow with less, basically with less resistance. A lower resistance path around bulb 2. So let me label all of this because we expect schematics to be labeled.
So
okay,
why is that necessary?
Why is what necessary?
That bypass.
Well, because it was in the directions of what I asked for on the schematic, but it's something we're going to use on safety controls as we move forward. It allows us to time out certain loads and bring certain other loads in.
All right. But that could exist without that, correct?
Like
that circuit could have, I mean, that would be a functioning circuit without that bypass.
If you were not following the sequence of operation that I put up in what I wanted on the circuit, yes, that circuit could function without it.
All right.
Okay, but part of this is drawing the sequence of operation that I asked for. Okay, so this is the schematic. Okay, now the thing is, the rest of our schematics are building from this one. Okay, this is a basic schematic, but as we continue down the path of our controls, the rest of the schematics are building from this one. Okay, now I do have a couple people who I suspect have had electrical from the electrician side of things looking at schematics. The schematics that you looked at in electrical are slightly different than the schematic we're looking at here. I need you to draw the latter schematics, because what you're looking at from the electrical side is more of a pictorial on how to wire it. It doesn't give you good sequence of operation. Okay, so please adjust how you're drawing the schematics. And that's part of why we're going to spend the time on this today. Okay, is there any questions anyone has on this schematic? Okay, and I'm just going to toss in my L in neutral. That was schematic of the day number 1. Okay. Then, schematic of the day number 2, we basically took this entire schematic, okay, and we adjusted it. Okay, so if we look at our directions on here, we still have 3 light bulbs. 2 light bulbs are wired in series. The third is wired in parallel to the 2 in series, and a single pole switch controls the whole 120 volt circuit. A second 24 volt switch will then bypass the second bulb in the circuit when closed. Add any additional components that we've discussed. Now at this time we did start already discussing the transformers. Okay, so in order to make this a 24 volt switch, I have to add a transformer to the circuit. Okay, so what I'm going to do, because I have a symbol sheet that I took the time to draw up, and I highly recommend you folks do this eventually. Okay, I'm just going to paste in the transformer, and we're going to put the transformer as a load in my circuit. Okay, let's see, mute. Okay, so now this switch has to change. Okay, I can't have this switch here because it's going to be no longer a line voltage switch. So I have to move my switch down into my 24 volt circuit. Okay, so I'm going to come in here and I'm going to wire my switch back. Move that over a little bit so I can get some wire in here. Now, what other components do I need to add to this circuit to make this work?
A coil. Yeah, a relay.
I got to put a relay in, right? So we're going to throw a relay coil in here. Okay, so I'm going to steal my relay coil that I've drawn up a few times. Hopefully this time it will copy properly. Cool. Okay, I'm going to toss my relay coil down here. Now, if I have a relay coil, what do I have to have?
Contacts.
I have to have contacts someplace that's connected to that relay coil. Okay, now, I'm going to label this whatever. Does it matter what I label it?
No.
No, it really doesn't matter what I label it as long as the label down here matches my label. Of course, that's going to go in the wrong place. As long as my label down there matches my label that I'm going to put up here when I get my contacts drawn in. Okay, so I'm going to put normally open set of contacts down there. Okay, now this circuit, will it do the same thing as the previous circuit did?
Yes.
What is our difference? Why is this circuit, if we're dealing with a control situation, if we're dealing with air conditioning, if we're dealing with, just a control situation in air conditioning, why is this circuit a better circuit for us to use?
Because you don't have to hunt down the bypass switch to turn it on and off. You can use the relay coil.
What about safety?
Oh, yeah, that too.
Your answer is not wrong, okay? But again, we're building towards our air conditioning circuits. So part of what we want to do is remember that the control voltage is what's going into people's houses. Okay, that's the whole purpose there.
Hey, Chris, I have a question.
Sure.
So when I drew my schematic from yesterday, everything looks almost identical to mine, except for I put my switch on the line voltage side towards the left. So it would introduce the power when you would close the switch to the transformer, which would then power the relay coil. Is that all right to do that? Because I was assuming it was a line voltage switch.
Well, it would have been okay had I not set a 24-volt switch.
Okay.
Okay. Yeah, I mean, it would have worked the same, but had I not set a 24-volt switch.
Okay, my bad. I mistake the 24-volt switch for a relay.
Okay. Yeah, I mean, the other thing, though, that I did see a couple people try to do was put a transformer right, I'm going to circle something. A couple people, well, I guess I'm going to circle something. Let me grab a circle. A couple people tried to put the transformer right there. Why would that not work?
Because it's on the line voltage side of the ladder diagram?
Well, if you wired the transformer in instead of where I had it right there, if you wired the primary of the transformer there, it would be on the line voltage side. But what is the problem with putting the transformer right there?
It's basically series with the other bulb, so...
It's in series with the other bulb. Your transformer will never get full power. Make sense?
Okay, dumb question. Why won't it get full power?
Not a dumb question. Okay, if you take I'm going to try to follow this through. Okay, I have line coming in here, right? I have line coming here. Now I have a load. If my transformer is wired where it is, all my voltage is coming through B2 to my primary of my transformer. So I have two loads in series. They're going to split voltage. Does that answer the question?
Yes, it does. Thank you.
Okay. So again, we got to be very careful that loads in series, okay, always split voltage, okay, and it's dependent on the resistance of the device. Transformer primary windings have a pretty low resistance, okay. Sometime when you get in the shop, take a resistance of a transformer primary winding. It's a pretty low resistance. So we just want to be very careful about not putting transformers in series with another load. We can put them in series with a switch, but not another load. Any other questions on this? Anybody draw something slightly different that you want to ask me about?
Can you tell me why the transformer is there?
Because the transformer needs to get full source voltage, okay? So we get full source voltage, and it creates the current for the secondary side of the circuit. Remember, I said a 24-volt switch will bypass the second bulb in the series circuit. Okay, so I have to have 24 volts, and therefore I need the transformer.
Okay.
Okay, because this is the first step. We're slowly building towards an air conditioning control system. We're going to get there today. But I needed you guys to start building this up to get to the air conditioning control system. Okay, one of the things, again, I want to stress is the difference between series and parallel. Okay, parallel, every load gets full source voltage. Series, the voltage is shared between the two loads. Okay, any other questions on this circuit?
I have a question in general just about the schematics of the day assignments. I had not realized that that was a thing. Is it possible for me, I know I can't get points for them, the late ones, the old ones, but like to understand this better, because I'm still a little confused. Is it still possible to access those old ones?
You can email them to me.
All right, I just wanted to like at least look at them, and maybe these will help me understand this, because I'm still.
The schematic of the day started with this one on Monday.
Okay.
This was the first one.
All right.
So you've had Monday, Tuesday, and I think today is Wednesday, if my calendar's right. So you've had this one, which we talked about today. If you want to grab a picture of that. If you want to grab a picture of that, you're more than welcome to. That was Monday's. Tell me when you got it if you're grabbing a picture.
I got it.
Okay. This was Tuesday's. We added the, let me shrink it down a little bit for you. We added the low voltage side.
All right.
Okay. And then today, what was that?
I didn't see anything.
Okay. And then today, for those of you who are on the call and paying attention, we're going to go through the one for today because I think it's so important, because I can't go further until we understand this one. Okay. So this one, basically, we're drawing a line voltage schematic that consists of two light bulbs. The two bulbs are wired in parallel. A single pole switch controls the whole 120-volt circuit. A 24-volt thermostat controls bulb 1, and a 24-volt switch controls bulb 2. Add any additional components that you need to make this work.
Would that be a heating or cooling thermostat?
Let's go with a cooling, considering what term we're in. I would have taken either, quite honestly, but let's go with a cooling, considering we're in an air conditioning term. So basically, just because I can, and if my little beach ball goes away, that would be awesome, I'm going to copy this same diagram down, and I'm just going to make a few minor changes. I'm going to get rid of my little bypass here. Okay, I'm going to get rid of my third bulb because I no longer need that. The directions aren't asking for it. I now have two bulbs. Okay, what do I got to throw in both lines before the bulbs to meet the directions of the circuit?
Put relay coil on B1.
Do I put a
Or
relay coil on B1 or the contacts?
contacts, relay contacts.
Okay, so let me jump over here and grab my contacts, because I'm not going to do a ton of extra drawing if I don't have to. Okay, so there's my contact for B1. Do I need something similar for B2?
No, you need a thermostat on B2.
Well, is it a line voltage thermostat or a 24-volt thermostat?
24 volt.
Okay, so am I going to put a thermostat up here on B2, or am I going to put it down in the 24-volt section?
In the 24 volt section.
That's correct. So I'm going to come over here, I'm going to grab my cooling thermostat. Okay, and I'm going to just copy it over here. It doesn't know where to paste it, it just does. Okay, so I'm going to come in here, I'm going to connect in my 24-volt thermostat. What else do I need on this side of the circuit?
A second relay coil.
Another relay coil, right? Okay, it's easier for me to copy it from over here. Ton of noise in the background, folks. Solve that problem. Okay, so I'm going to throw this relay coil in here. Now, can this relay coil be labeled the same as the other relay coil, or do I need to pick a different?
Different.
I need to pick a different label, right? So let's call this, I'm just going to call it CC, and you'll see why in a minute. I'm just going to call this CC, and I'm going to change the label of this one to FR, and I'll show you why as we move forward. Okay, we're going to label just this as cooling thermostat. Okay, I'm going to come up here. If I have a CC down here, does one of these sets of contacts have to be labeled CC?
Yes.
Okay. What about FR? Does one of them have to be labeled FR?
Yes.
Okay. Labeling starts becoming relatively important. So,
what does the FR stand for?
we're going to call it. It's just a relay label, but in this case, it's going to end up being our fan relay.
All right.
Okay, as I move forward. And my CC in this case is going to be compressor contactor as we move forward. Okay, now, this is a good question because someone actually sent me an email yesterday on the labeling. Okay, how do I pick label names? Does anybody know how I pick label names and what I'm going to label things? Anybody want to guess? It's okay to guess wrong.
I guess whatever relay is going to control whatever contact.
Yeah, I just picked the labels based on, okay, if I know eventually that relay is going to control a fan, I'm just going to pick something that I can remember that it's going to control a fan. So if I have an FR for fan relay, I know that I can look at it and guess fan relay. Okay, there's no scientific approach to naming these things. There's no way you have to label them. You can label them what you want as long as whatever you have labeled on the control voltage side matches what you have labeled on the line voltage side. Okay, you could call this whatever you want. It could be DT or whatever, as long as it matches. I have a tendency to pick labels that somewhat go along with what this device is going to be doing. If that makes sense. Okay, so labels, they're not set in stone what they have to be. Okay. Who can tell me what the sequence of operation of this circuit is? What does it do?
When the thermostat calls for cooling, it closes the contacts on the contactor, compressor contactor, which will then close those contacts and energize B1.
Okay, keep going.
And then I guess the switch on your thermostat that you can turn your fan control on and off with, when you select that on the 24-volt circuit, the fan will come on, which will energize B2.
Okay. Extremely close, okay? To the point, I'm just going to make one suggestion on your, okay? Let me walk through it and see what you missed. Okay, because it was so close. Okay, see, when service switch is turned on or closed and CT calls for cooling, it will energize the CC relay, which closes the normally open CC contacts, energizing B1. When switch SW is closed, it energizes the FR relay coil, which closes the normally open FR, which energizes B2. Make sense?
Yes.
Anybody else have questions on this?
I'm just trying to copy it on a piece of paper right now so I can
do like switches and thermostats.
I'll give you a minute.
You
tell
still
me
got
when you're done.
bulb number 3 on there.
Yeah, because I forgot to delete the label. I might have accidentally done that on purpose. Someone yesterday handed in a picture of the diagram that I did on the screen.
Now, I was just curious, do you always have to put labels on switches and thermostats? Because a lot of times there's a lot of coils and contacts. I tend to leave it for those so it doesn't get confusing.
Label everything. Label everything.
Fair enough.
Because when you start getting into, heavy control circuits like building controls and stuff like that, if you've gotten in the habit of labeling everything, you'll never mess up.
Okay, good point.
A lot of this basic stuff that I'm doing with you guys, and part of the standards we're setting, is to make sure you get in the habit of doing it right so you never do it wrong when you're rushing in the field. That's a good portion of what we're trying to instill, is so that everyone gets in a habit of doing it right. I'd rather you lose 10 or 20 points on a schematic for doing it wrong than when you get in the field have an employer get pissed off at you. So that's just my opinion. Whoever was copying it, tell me when you're done with copying it so that I can move forward.
I'm done.
Okay. Anybody else need me to wait a sec? Okay. Let's start a little bit talking about motors. Now, in real life, of course, B1 and B2, we don't want to just turn on a light bulb in order to air condition. Okay, first of all, light bulbs give off heat. Second of all, it would be pretty stupid for us to do that. So the reality is all of our light bulbs in our circuits are actually going to be motors. Okay, now, there's a difference between the schematic that I have here and the pictorial we're going to talk about here. Now, some of you guys have seen this stuff before. Okay, I call them connect the dots, and they're actually pretty good from a wiring standpoint. Okay, what we do is we look at these screens. These are all the components, and it says basically connected for proper operation. Now, there's two components in here that I just want to introduce. We're going to talk much more about them as we move forward. We have the capacitor, which is right there, and we have our split-phase motor that's right there. For the moment, just accept that this is a motor, okay? And accept that it has two windings in it. One winding has a resistance of 5 ohms, and the other winding has a resistance of 14 ohms. These resistances are taken by taking your ohm meter and going from common to each of the other terminals. Okay, so from common to that terminal is 14. From common to that terminal is 5. Okay, a capacitor, in the grand scheme of things, to make this the short side of the capacitor, okay, it stores and releases electrical energy. Okay, again, a capacitor stores and releases electrical energy. And again, there's way more to talk about capacitors, and I know a couple of you guys have had electronics before. We could go much more into capacitors, okay, and we're going to. But it stores and releases energy. Now, one of the things I talked about way back when we talked briefly about is that we have current that flows in what we call a sine wave. Okay, if this is neutral, what I just drew on here, or basically 0, your wave pattern goes like that. This might be, this point up at the top of it might be 120 volts. At the bottom of it is negative 120 volts. So 60 times a second, it makes a complete revolution. By complete revolution, what I mean is it starts off at 0, and then it comes back to 0. In other words, it's a full circle, 60 times a second. Which means that 120 times a second, you are passing through 0. Now, what can you tell me if you have line 1 at positive 120 and line 2 at negative 120? What happens when this current passes through 0? What happens to anything attached to it when this current passes through 0?
It creates a charge?
No, it actually doesn't have a difference in potential. Okay, all of our voltages is based on having a difference in potential, either between 120 and neutral, which is the center point, or 120 positive to 120 negative. Everything we do is based on having the difference in potential. Now, everybody knows magnets have north and south, correct? Okay, everybody, we should know that a magnet has a north and south pole. Okay, now a motor operates on magnetic principle. It operates on this idea of north and south because two south poles repel each other. A north and a south attracts each other. So as this magnetic field is shifting 60 times a second, that's what's driving the motor to go in a circle. Okay, because again, two like poles repel each other, and two unlike poles attract each other. So 60 times a second, this magnetic field is reversing. But right here, where the current goes through 0, at my x's, okay, where it goes through neutral, the magnetic field collapses. Okay, there is no magnetic field for that split second. It just collapses and basically dies. If my motor is caught between two positions, if my motor has a heavy load on it, it becomes very inefficient because the entire magnetic field collapses where this goes through zero, where I suddenly have zero potential, zero voltage to the coil, and zero magnetic field. Now again, it's just a split second in time. Think about it, 60 times a second. That's not that great of a time period, but it's enough to affect the efficiency of a motor. So our purpose of putting a capacitor in is that capacitor, as it charges and releases about 70 to 90 degrees out of phase with my main power supply. Okay, and again, my drawing's really, really bad. It's a much smoother sine wave. But one of these windings is connected to the capacitor, and it releases the current about 70 to 90 degrees out of phase with the main current. What that does is it means that no two windings in the motor are getting 0 volts at the same time. I always have a magnetic field in that motor. And the whole thing that does that is that capacitor. Okay, I always have a magnetic field in that motor. Any questions on that so far?
I do, but I don't want to confuse a lot of the new guys in here. I was just curious about typically on like a 120 volt circuit, if you were to read that on a scope, kind of like you drew it, you would get something more like 170 at the peaks, would you not?
Yeah, you get peak voltage, yeah.
Okay, all right, cool.
Yeah, I'm going with the average.
Yeah, no, that makes sense, and I know that's what you'll measure between any of those points is like 120, so.
Yeah. If you looked at it on an oscilloscope, it would be showing higher than that just because, again, it spikes a little bit more.
Gotcha.
Okay, any other questions? Go on.
Are those three symbols there, those three drawings, those are all examples of what you're talking about? Like that's how you'd see it drawn?
You would see it without the circle around it if you were looking at it in a ladder schematic. Okay, if you're looking at it in a pictorial like this is, a wiring diagram, you might see them with the circles. But when we draw it in a ladder schematic, we're not going to draw the circles around it.
Are there any other names for them?
What, this type of drawing?
Yeah.
I've always heard them referred to as a pictorial or as a wiring diagram.
All right.
Why, did you hear something else someplace?
No, I just trying to do my own research on drawing ladder schematics and stuff, and it seems like there's a varying array of ways that people do it. Like they don't all look the same.
No, they don't, unfortunately. Okay, a lot of people these days are crossing wiring diagrams and ladder schematics together, sort of as a hybrid sort of thing. A lot of companies are making it, are basically trying to save ink on some of their diagrams, and it's become a real big issue. So we have to work with the base that we have and just go from there. Okay, this symbol right over here that oops, let me get my pointer back. Okay, this symbol that I'm pointing to right here is a capacitor. This symbol that I'm pointing to, okay, that I'm moving the pointer to over here is a split phase motor. Now, after we wire the capacitor, this motor changes its designation just from being a split phase motor to another type of motor. But again, two basic symbols, capacitor and motor. When you draw this into your ladder diagram, it's going to look slightly different, and I'll show you that in a minute. Okay, this is a cooling thermostat. We've already talked about that. So when we wire this diagram, basically what we're wiring is the thermostat. In this case, it's a line voltage thermostat, is directly controlling a motor. Now, placement of the capacitor becomes very, very important. I'm going to give you two basic rules on this. The lower resistance winding is considered my run winding. The lower the resistance winding is considered my run winding. The greater resistance winding is considered my start winding. My run winding always gets direct power. Okay, run winding always gets full source. My start winding is in series with the capacitor. This starts to become very important with series parallel. So again, my run winding, which is the lower resistance winding, always gets full source. The start winding, which is in the series with the capacitor. Okay? So be careful when you're looking at these motor diagrams. You will never bring direct voltage to the greater resistance wire. It always goes through either a capacitor plus a switching device. Okay, and we're going to go into a little bit more of that, but the basic setup of the motor is run gets full source. Nothing is in series with run. Well, 99.9% of the time, nothing's in series with the run, other than a switch. Okay? My start winding always has something in series with it. So in this case, what I'm going to do is let's go ahead and wire this. Okay, I have my line coming into my thermostat. Let's keep that easy. Out of my thermostat, okay, I'm going to come down and I'm going to connect my run winding. Okay, but I'm also going to provide power to my capacitor, which is going to connect into my start winding. Okay, and then we go back to neutrals, and I'm just going to go ahead and label neutral, line of neutral. And since this is permanently in the circuit, there's no switching before or after this capacitor, this becomes what we know as a run capacitor. It stays in the circuit. And again, we're going to spend more time on this when we go through the formal motor presentations. But I wanted to introduce these concepts today. So again, start winding always has the higher resistance. Run winding has the lower resistance. The capacitor always goes in series with the start winding. The run winding, 99.9% of the time, gets direct source voltage out of whatever switching device you have. Any questions?
No questions. I'm just drawing this real quick.
Yep.
I'm sorry, can you repeat what R stands for again? Thank you.
Run.
Oh, okay, thanks.
Again, the smaller resistance winding is always going to be my run winding. Oops. Tell me when you're done drawing so I can, I'll go on.
The symbol for the run capacitor is always going to be that symbol?
Be careful about the dot, okay? A lot of the capacitors shown on schematics these days will not have the dot. So a lot of times what you're just going to see is a variation of it where you're just going to have that.
Okay.
Okay, you don't always see the dot anymore. And the reason you don't always see the dot anymore is because you just have to remember as a technician that if you don't see any switching devices, and I'll show you that in a few minutes, if you don't see any switching devices around the run capacitor, you know it's a run capacitor. If there's switching devices, and again, I'll show that to you, everybody, in a minute, it's a start capacitor. And I never know which to introduce first, capacitors or motors. So this time we're just introducing motors first. We'll get back to talking much more about capacitors. Sort of like the chicken or the egg, which came first. So
I have it all copied now.
Okay, is anybody else still copying? Okay, you see my little drawing down here with the circle and the 3 dots? Okay, this gets sort of important. If you walk up to a compressor and it's not labeled, okay, this is what the connections on a compressor look like. You have 3 basically pins looking on the side of the compressor. Okay, 3 pins. You don't have a label on there because the labels will fade off eventually. So sometimes we need to figure out what is next on the compressor, what winding is what. So what you're going to do, you take your ohm meter and you take resistance between each of the 3 pins. Okay, so like between these 2 pins, where I'm going to write a number, is 14. And that's 14 ohms. Between these 2 pins is, let's go with the same thing the motor has. Let's call it 5 ohms. Okay, so you're taking between the 2 pins. Okay. Now, you have a third reading. Okay, that's going to be 19 ohms. Whenever you have this situation where you've had to take the 3 readings, the pin across from your highest reading is common. Okay, again, you've taken 3 readings between all the pins. The pin across from your highest reading is common. From common to your next highest reading is always going to be start. From common to your lowest reading will be run. You're going to do this when you're in shop and have a whole bunch of compressors sitting in front of you, some busted, some not busted. So again, say this again. You take 3 readings from each pin to each pin. You have your highest reading, the pin that is across from that highest reading, okay, or the wire that's not included in the highest reading is your common. Once you identify common, the next highest reading goes from common to start. That's this winding up where I have S up in by the run capacitor. The lowest reading is from common to run. why do I know that my highest reading is going to be from start to run? Why do I know that?
Because you're getting source voltage?
This is the resistance. My highest reading is between start and run. Look at the motor up top. Tell me why my highest reading is from start to run.
They have to stay separate.
It's a combination of the two.
Thank you. When you're reading from start to run, you are reading your resistance of both the start and the run winding because they're connected at common.
But
okay,
isn't
so
it subjective to say that? I mean, how do you know, looking at this, that the highest reading, or that the contact that you're going to read is the 5 or the 14?
You don't until you take the readings. Okay, so if I were walking up to this and didn't have my readings in advance, I would take 3 readings across the 3 pins. Okay, I would write it down on a piece of paper because you're not going to remember them all. And then I would look at the piece of paper and I would say, okay, I have 19 ohms. The pin across from the 19 ohms is my common.
Okay.
Does that make sense?
Yes, I understand now.
Okay. Any other questions on this? Because this is... Anybody else? Because this is sort of important.
So the 2 lower numbers will always equal to the highest number in resistance.
Within an ohm or 2. It's going to be really close. Okay, sometimes, remember, I don't know if I said it to this group yesterday or not, over time as the battery in your meter gets weaker, sometimes your readings get sort of strange. Okay, the battery in your meter makes a big difference on how accurate your readings are. So as your battery gets weaker, I might have gotten 14 and 5 and maybe 18. 14 and 5 and maybe 21. It all depends on, but it's still close enough where I can say. Okay.
So the contact across from your highest reading is common.
Is always common, yes. And remember, my readings are between the pins. That's why I have written where I wrote my ohm readings. Because it's not on a specific pin, it's between 2 pins. Okay, so again, that explains why we know up on the motor at the top of this that C is common, because we have 14 and 5, so basically I would have taken the same readings down here if the motor wasn't labeled. Okay, this is very important when you start troubleshooting in the field. This is something you want to remember, not just for this course, but this will help you out moving forward. Questions on this before I move on? Okay, so I want to skip back to this diagram right here. Okay, I'm going to skip back to this one. And I'm going to remove B2 from the circuit, because I'm going to make a slight adjustment here. Okay, I'm going to go over to my motor, to my schematic cheat sheet, which once again, I encourage everybody to eventually make yourself a schematic cheat sheet, because it saves a lot of time, and you've drawn them, so I'm fine with you using it. And I'm going to copy in my motor with a single capacitor. And I'm going to do some slight rearrangement. . Okay. That's how you would draw that motor that we just had on the other diagram into a schematic. This motor and this capacitor is now drawn into this schematic. And we could call this motor indoor fan motor. Okay, and that's exactly what I'm going to label it, IFM. This would be the motor in your air conditioning system that blows the cold air around the house through the ductwork. Questions?
Yeah, where can I find like a cheat sheet like you have there?
I made it. There's no way to really, and it's a little early in the term for me to just make this publicly available because I really want you guys to learn how to draw these schematics. I just created it. I don't know if there's anyone if anybody has posted it yet to the internet. I will tell you guys that probably in about another week or so I'll make it available, but in the meantime I really need everybody to learn how to draw these symbols. And if you look at your symbol sheet that we did way back when, that you guys did as a lab, a lot of these symbols are on that. But not in a way you can copy and paste because they're just not set up for that.
I do have a question.
Yeah.
Why wouldn't you set up the relay for the cooling thermostat to the motor?
Because I still have to, and you'll see it when I put in a thermostat, when I put in a real thermostat here. But remember that you have that auto and fan on switch on most of the thermostats. I don't want to lose track of that fan has to be able to be controlled separately.
Okay.
Okay, this is not exact yet down in the control section. This area down here at the bottom is not exactly what you will find, but we're moving in that direction.
Okay.
Okay, we still have to deal with the whole switching of the thermostat side. Sorry, if I don't go baby steps, I'm going to lose a bunch of people, and I don't want to do that.
That's fine, thank you.
Okay.
I just want to double check the symbol that separates the two main boxes here. That's a transformer. The
yeah.
120.
Yeah, this is a transformer that I've labeled that it could either do 120 or 240. Okay, it's just how I have it labeled on when I drew it out originally. Anytime you have two windings and the two bars between the middle, that's a transformer. You see the two straight lines between the two windings?
Yeah.
That's the symbol for a transformer.
And the two parallel lines,
yeah,
the CC and FR, no, CCFR, those parallel lines. What is that?
That's a normally open contact.
I don't have that on my thing.
There should have been one near the top left of your symbol sheet. It was probably part of the contactor or relay.
Yeah.
Okay, you should have had a normally open, that's to two lines, and a normally closed, that has a slash through it.
Okay. And then the IFM, the fan symbol you have there, I don't see that on this sheet.
Okay. Your motors aren't on that sheet? I thought it was. Okay. This diagram right here. Let me put a box around it. Actually, let me switch over to my sheet here. This is a diagram of a permanent split capacitor motor. Okay, we have a single run capacitor that is always in the circuit. Okay, don't copy the others down yet because we haven't talked about them yet. But the permanent split capacitor motor is a single capacitor that's always in the circuit. And we're going to spend more time on the motors, so I don't want to dig deep on that right now. Okay?
I'm almost done copying it. And the little squiggly lines, these are windings?
It's just a winding, yeah. My windings look like crap on this because I haven't figured out how to draw little squiggly lines yet. Definitely not an artist.
That's a permanent split capacitor.
And you'll always see that as a PSC. No one really spells this out. It's just a PSC.
All right, I got it.
Okay. So we now basically, we have one light bulb left that I really want to do something about today because it's, again, useless to have a light bulb in a cooling circuit. So I am going to jump over back to one of my little wiring diagrams, or I call them to connect the dots, and we're going to talk about one other type of motor. Okay? This type of motor, we still have our standard motor that we talked about over here, right? This is the same basic motor, except my diagram is 12 and 5 for resistance. Which one of these is my start winding?
The 5?
12.
12.
The 12. The one with the greater resistance is always going to be my start winding. 5 is going to be my run winding. So what winding does my capacitor have to wire into?
It's a higher one.
The start winding, right? So if I label this out, my start winding is there, my run winding is there, and my capacitor has to come into my higher resistance winding. Now, this is a different capacitor. Can anybody tell me how I know that? This is no longer a run capacitor.
Because of the dot? It's a start?
Well, it's missing the little dot, but if I saw this in a circuit where people aren't drawing dots, how would I know that this is a start capacitor? What about the switching device?
There's a switch ahead of it, so it means it's a starting device.
Anytime you have a switching device, okay, in a circuit with a capacitor, okay, it is a start capacitor. This type of motor is known as a CSIR motor. The start winding is no longer in the circuit once the motor starts running. Let me wire it. Okay. Going to do the easy part first. There's a reason I'm telling you guys to do the easy part first. Okay? That way you never mess it up and go to the wrong winding. I see a lot of people who insist on taking putting the start capacitor in series with the run winding instead of the start winding. Don't do that. Okay? So what we're going to do is we're going to come down, and I have to do a little bit of jumping around on this one because I'm going to have a wire crossing. Okay? I have that. Okay? My neutral, we know where my neutral comes in, but again, I'm going to give myself a little bit of room on this one just because of a connection I have to make. Okay, now what comes over to my run winding? What connects into my run winding? What did I say is the rule for run windings?
It gets full power, so it comes right from the switch, or right from the line.
It gets full power. Don't get caught into putting anything in series with that run winding. Okay, run winding, full power. Now I have one extra pin there, right?
You do?
Anybody see the extra pin I haven't used yet?
A 5.
Number 5.
Okay, this pin, oops, I didn't mean to change that color wire. Let me fix that. Okay. This pin comes over and connects into common.
So is that a ground?
Not a ground. Connects into common. I'll explain in a second. Let me get this wire in, then I'll explain. I do a few little labelings here just before I forget.
Will a CSIR always be drawn that way?
A CSIR will always have some sort of switching to take out the start capacitor. It might not always have this device. There's about 4 or 5 different switching relays. Okay? This is just a switching relay. This one is called a potential relay. And again, we're going to dig into this deeper, folks. So don't worry if you don't totally get this to start with. This is just sort of an overview so that I can get you in the right direction. Okay, this is a potential relay. Has anybody in this group had potential relays before? I know some of you may have had refrigeration already. Anybody?
Yes, we did.
Yeah, we talked about it.
What can you tell me about a potential relay?
The back EMF off the common terminal of that compressor is going to energize the relay coil and pull the start winding out of the circuit.
Correct. Okay. So what happens here is when we have we have a magnet spinning inside a coil of wire, right? We know that a motor is a magnet spinning inside of a coil of wire. We know that because I just talked about it a little bit earlier. Okay, as that magnet is spinning in a coil of wire, it generates electricity. Okay, even though we're providing electricity to the circuit, it still generates electricity on this start winding. Okay, this start winding starts generating its own power. Okay, that power is captured by this potential relay coil that's right there. That ties into the start winding and the common. As the motor starts spinning, when it reaches about 75% of its speed, it actually has enough power being generated off this start winding that it opens this normally closed contact and it takes the start capacitor out of the circuit. Okay, why is that important to take that start capacitor out of the circuit? Because the start winding in this type of motor cannot be left in the circuit. It will burn out. It's very specifically just designed to start the motor. Okay, the start windings has a very fine winding, very fine windings. Okay, run windings are a little bit thicker. They're more durable. But start windings are specifically designed in these motors, in CSIR motors, to come out of the circuit. The other thing is, this is a pretty powerful capacitor. Okay, run capacitors, the ones we've been talking about previously, they go basically from 5 to 60 microfarads. Microfarad is the measurement of capacitors. Start capacitors usually start at about 125 and go up to I've seen one recently, 275 microfarads. Okay, microfarad is the strength of the capacitor. You cannot leave a start capacitor in the circuit. Okay, two bad things will happen. One, you take a chance of burning out the motor winding, and the second thing is start capacitors have a tendency to blow up if they get it too hot. So those two things should tell you don't leave it in the circuit. So as soon as this motor starts spinning 75% of its speed, it will actually open up, okay, by having enough what we call back EMF to open that contact between 1 and 2 and take that start capacitor out of the circuit. Okay, EMF, remember, it's voltage. Potential is voltage. Okay, so this is all working on this potential relay. Okay, and on the back EMF on this motor. Okay,
so will
question.
Will that line always be there when you draw this? Should you always connect the potential relay to the
common?
Yeah, the common.
Yes. Every potential relay you will ever see from a supply shop actually has 3 pins on it that are labeled 1, 2, and 5. That is a dead giveaway. It's a potential relay. It will be labeled with pins 1, 2, and 5 as a standard. 5 always goes to common, 2 always goes to start, and 1 always gets connected to your start capacitor.
Okay.
Okay, so anytime you see, if you happen to see on a test or something like that, that's eventually going to happen. If you see 1, 2, and 5 and you're asked what type of relay is it, it's easy. It's a potential relay. It's the only relay that is wired this way. It is probably the most heavily used relay for starting and motor control that in the entire HVAC industry. It's used on all air conditioners that have start capacitors. Okay, don't see it that often used in refrigeration, but in air conditioning we use it very heavily.
So, I'm just making notes on this potential relay. What did you say? 1, 2, and 5 are always gonna. So 1's always gonna be power.
No, 1 gets connected to your start capacitor, which is powered.
Start.
2 always goes to your start winding. And 5 always goes to common. I'd like to do one more thing before we end today's call. I really want to go stick this motor into my schematic I've been drawing. So tell me when you're ready.
I'm ready.
Does anybody else have any questions on this drawing the way I have it right here, this pictorial or the wiring diagram? Okay. I want to jump back over here, and I'm going to modify this now. Okay? So what I am going to do, I'm going to replace that light bulb now with two components. Okay, I'm going to replace that light bulb with my potential relay and a motor. I think I'm going to, actually, I have a drawing right there that I'm just going to use. Maybe. Now, don't copy this quite down yet. I got to get rid of a capacitor that's in here. Need to make some slight adjustments. Okay, this is the corrected diagram, and this would be my compressor. And that is how you would see a potential relay with a CSIR motor drawn on a ladder schematic. Anytime I see a device that says 1, 2, and 5, it's a potential relay. Anytime I see a capacitor symbol connected into pin 1 of a potential relay, I know it's what type of capacitor? Start capacitor. Questions? I know somebody has some.
Do you have to label your Rcns different for each motor?
It's again, do you have to? Usually not. You just want to be able to, not differently. Do I always draw the run winding at the top? Yeah. Do I always have the common out to the side? Yes. Do I always have the start winding down at the bottom? But if I don't have resistances, if I had the resistances here, like 15 or 5 or whatever it is, I wouldn't worry that much about labeling. But it's a good habit to get into to label start, run, and common. So again, when you look at this in the field, will you always have everything labeled when you grab a schematic that somebody else drew in the field? No, but does it help? Yeah. For the purpose of this course, do I expect everything to be labeled? Yes. Any other questions? Guys, I've gone through a ton of schematics today. It's very important that you start practicing drawing these out. I know you guys took pictures of this stuff. Just to toss this out there, please don't turn in my pictures for your own schematics. I've drawn these. I know what they look like. I really want everybody to be able to draw your own schematics. It's important. So that's all that I have today. Anybody have any questions for me?
I just had a question about discussion